Is it for? Yes. Yes. Okay, sorry. If you don't mind, as I'm Italian, I have to point stuff, so I'll stay here. So I'm sorry, but as I don't have a pointer, I'll do like this. Okay. So yeah, this talk is, I mean, it's a bit different from the one that you saw. I would say online, but the idea is a bit the same. So there will be a presentation on some activity that we do within the QUTAC working group of material science. And I will not say what QUTAC is, because I think there were already some talk that were presenting the activities of QUTAC. I will just say that one of the working group in QUTAC is the working group of material science. And what we do there is to somehow try to identify, develop, test, and share potential application of quantum algorithm for industry-relevant use cases. Okay. So what's the problem? So you know, in quantum chemistry, in material science, the aim of some of the algorithms is trying to find what's the most favorable, the most stable state, for example, of a battery that is a very interacting state, a very interactive system, or for example, a molecule like this one. Now, what's the problem? The problem is that in general, the ground state configuration, that is the configuration that has the lowest energy, is not described by a unique state that tells, for example, which electron belongs to which orbital. But the ground state of this molecule is somehow a superposition of many of these states. And the problem is that the superposition is most of the time entangled. This means that the correlation that there are among all these electrons are very, very strong. And if you want to get a precise description of this system, you need to use methods that are somehow not really classical, but that should, I mean, we believe that should be run on quantum computers. Now, what's one of these methods? In general, what is done is in quantum computing is using what's called the variational quantum eigensolver. This algorithm is an hybrid algorithm, so somehow there's a part that runs on the quantum computer, and this part somehow contains the ansatz that will be written such a way to respect, for example, the symmetry of your system. But this is an hybrid algorithm, so part of this algorithm will run on a classical computer. And what the classical computer will do is try to find the minimum of this functional. And the parameters that are here optimized are the parameters that will better describe the ansatz on the quantum system. Now let me do a bit of advertisement. So somehow this is a very recent work that was done by some colleague of us at BASF in collaboration with some university and some scientists from the Austrian startup QT. And what they were able to do here was to solve via a modified VQE that contains somehow a standard VQE plus some classical post-processing of the data. So they were able to find, within chemical accuracy, the ground state energy of an industry-relevant system, namely an iron compound that BASF, that it's one of the products that BASF is currently selling. But we know, unfortunately, that this type of algorithm suffer about a problem that is the barren. One of these problems is the barren plateau. That is somehow says, I mean, this problem says that the gradient of this functional with respect to this parameter can be very, very flat. So if you want to optimize this functional, you won't be able to find a good minimum for that. So that's why in QUTAC, in this working system QUTAC, we try to find alternatives that are kind of beyond-NISQ or early-fault-tolerant to VQE. And I will briefly describe three of them. The first one is quantum enhanced version of a Monte Carlo technique. The second one is a quantum imaginary time evolution. And the third one is very recent. It belongs to a class of algorithms that are called randomized algorithm. So let me start with the first one. So the idea of this auxiliary field quantum Monte Carlo, this quantum enhanced version of quantum Monte Carlo, came from a paper by Google of some years ago. So Google, some researchers from Google, they were able to compute the ground state energy of some compounds by using a hybrid approach that was based on quantum Monte Carlo, but that was using a very complicated, a very entangled wave function. And I will tell you in 1 second why this wave function is used. But the basic ingredient, anyway, of this algorithm is what's called an imaginary time evolution. And imaginary time evolution, just a few words about it, because this will be relevant also for the second project. So let's say that we want to target the ground state psi 0 of a given Hamiltonian H. But of course, we don't have psi 0 at end. So what we generally have is an initial state that can be, for example, also a very optimized mean field Hartree-Fock state. Now you know that you can expand each of these states into a series of by using all the ground state and all the excited state of our Hamiltonian H. And this expansion, of course, will have some coefficient, and we somehow would like to distill from this expansion only the state psi 0. How can we do this? Okay, we can use this operator. It is a strange operator, is e to the minus beta h. But why this operator can be used like this? Because you imagine that beta is very, very big. You can apply this operator to your initial state phi I. And what you have is that you have a superposition in which the ground state won't be suppressed, while all the other excited state as E1 and will always be bigger than A0. The same for A2 and so on. You'll have that all these superposition will be exponentially suppressed. And what you will have is only this state psi 0. Now you see this is a bit different from what we do in general in VQE, because here you don't have any type of classical optimization. Everything happens directly on initial state and happens still on a quantum level. So that's why we believe that this could be a kind of better technique than VQE. Okay. Now, what we do with this projection? Okay, what we can do is that, for example, we can compute the expectation value. So we want the expectation value of the energy on this projected state. But what generally is done in the literature is that you don't do the expectation value by computing the expectation value on two projected states, e to the minus beta h phi I. But what it has been found in the literature of quantum Monte Carlo is that if you use this type of mixed expectation value, the estimate of E0 will be unbiased. Now, what can be this psi t? This is a bit somehow. I mean, this is somehow is a problem that is still relevant in quantum computation for quantum chemistry. Is that this is somehow a chicken egg problem. If you would have a very, very nice psi t, this E0 would really be equal to the energy of this state. But in general, you don't have this psi t. But what we can do, for example, you can implement this psi t as, for example, a unitary coupled cluster, and this can be done. This is supposed to be easy to be done with the quantum computer, and that's what Google did in their experiment. They used the simplified ansatz for computing this trial wave function, and what they were computing on the quantum computer was were these overlaps between this projected state and the trial state. And this can be done, for example, they did it by Hadamard test, or this can be done also more with some better technique like shadow techniques. So what we did was try to implement and test this method in two relevant cases. For one was for oxygen allotrope, so we were trying to find a gap between the ground state of the oxygen and the first excited state, the triple state of the oxygen. And also we were looking at some models that came from the described magnetic system, this copper bromine compound. Then after that, we were interested in understanding what's the classical cost, the classical in quantum cost, for example, of implementing the Hadamard test and the shadow technique. And if you're interested, this is the most recent paper that does this study. Okay. Now again, I say that imaginary evolution, that this is very relevant because this is a method that does not use any type of classical optimization. So we were interested in our second project in is it really possible to implement this projection operator directly on a quantum computer? Now the problem is that this operator is not unitary. So this is if beta is very, very big, this is a projector. but there was a paper also by Garnet Chan and collaborators that was able to approximate this unitary operator this non-unitary operator with a unitary operator. Now, I won't give you the details of this, but there's a way for solving this type of state equation. For each step of your imaginary time evolution delta tau, you can find an Hermitian matrix A, such a way that these two states, the projective state and this unitary evolved state, are equal. And I want just to mention that finding this operator A is somehow simple, because for finding this operator A, what you need to do is just to solve a linear system. The linear system can be exponentially the number of qubits or the number of basis state, but still this linear system will have a unique solution, and will not the method the technique for finding the solution of this linear system won't rely on any classical optimization. Now I will briefly show some result on that. But if you're interested, there's a recent archive by some of collaborators of this working group. And somehow we can see that there are two somehow different behavior. If we apply this QUTAC, this quantum imaginary time evolution, to an Heisenberg model with nearest neighbor interaction, and this is this first plot. So you can see here that if you compare so this is the fidelity and the energy as a function of the evolution time tau. The solid line is the exact time evolution. The blue line is this imaginary time evolution implemented via a unitary operator. And you can see that in the case where you have local interaction, the energy goes down and the fidelity goes up. So this, I would say, this can be a method. We believe that this can be a method if you want to do a state preparation for a model that has local interaction. Different is the case if instead we want to prepare the ground state of a molecule, for example, this iron compound or oxygen. And in this case, these are the result in this other plot. You can see that we already start from a state, this is an Hartree-Fock state, that has a very high fidelity and also a very low energy. But when the time evolution goes by, you see you are not able to reach, the fidelity goes down and also the energy goes up, meaning that you are not able to produce a very, very good quantum state in the case where you have not local interaction, like you can have, for example, within the orbital of a molecule. Okay. Now, last project, this is very recent, so I will not have a lot of results. Actually, I don't have any result on that yet. We don't have any result on that yet. But this is a way for doing, for computing, for example, expectation value of a given operator on the ground state of a given Hamiltonian H. And what we have as an input is, of course, the Hamiltonian and also a given state that has a given overlap with our true ground state phi 0. Okay, now in general, this problem has two sub-problems. One is really estimating the expectation value on a given state. The other one is finding a way for approximating this state psi, so find an approximation of the ground state phi 0 by starting from a state psi. The first problem in general would be solved when we will have a fully functional error-corrected quantum computer. We will solve it via quantum phase estimation. In the case, for example, where the operator rho is the same Hamiltonian H. But of course, you know that doing a quantum phase estimation has a huge overlap, has a logarithmic overlap in one over the error epsilon. So we scouted a bit the literature, and we found that there are a class of randomized algorithms that have a very low overhead. So you don't need a logarithmic number of qubits, you just need one qubit more. But the price that you have to pay is that you have to find an expression for the operator that you want to measure, for example, this unitary operator, e to the minus h. You have to find an expansion that can be written like a convex combination of unitary operator omega j. And this in principle is always possible. And what's also nice in this technique is that in general this operator omega, the operator w, they don't have a huge non-Clifford number of gates. Now, what's the idea behind this randomized algorithm? The idea is that you, if you can write this operator like this expansion, where these gamma are all positive and they sum up to 1, you can think about this as a probability distribution. So what would you do? You would sample one of these possible gamma. You run a standard Hadamard test, not with all the operator U, but the operator W corresponding to the gamma that you have sampled. And then, as computing the expectation value is a linear operation, you can reconstruct the expectation value just by summing up all the different contributions that you get while you were doing this sampling procedure. So somehow this solves in part the problem of computing the expectation value of an operator in a randomized way. The other problem was finding the ground state of the Hamiltonian. So yeah, I won't give it into much details. I mean, this is after lunch. This is not the best, but the idea is that we can use a kind. Oh, sorry, this should be a square here. So we can use a generalized projection operator, and we can transform these via its Fourier transform into a sum of a lot of unitary operation. You can plug this operator in. And this corresponds, of course, to projecting the initial state psi onto the ground state of our Hamiltonian H. Here you see you have an expression that looks like still an expectation value of this quantity that you can measure on your quantum computer times these weights. And you can always do the trick that you can always rescale this to be a probability distribution. So the idea would be the same. So we can sample 2 terms from this distribution. We can run a modified Hadamard test. I won't tell you why this is true, but if you do the math about that, you'll see that you really are able to compute this. Here there's a dagger missing, sorry. You're able to compute this expectation value. And you can repeat this a lot of time and reconstruct the expectation value of the operator O on the ground state phi. Now, this is still somehow a work in progress, so we don't have a lot of result on that. But what we'd like to do is understand if there are, for example, industrial relevant application, what's the cost of running all of these when we'll choose as a state phi 0 and operator O something that is relevant for industry. So this was my last slide, and thanking you for your attention.
Yeah.